deriving the first equation of motion, which is otherwise called as the velocity-time relation. We have already seen what it is. It is v equals u plus at, where u is the initial velocity of the body, v is the final velocity of the body, a is the acceleration, and t is the time taken by the body. So here I have a velocity time graph, which is a straight line AB. Now this velocity time graph gives us an impression that the body is moving with a uniform acceleration. So our first step towards deriving this relation would be to draw two perpendicular lines from point B, one towards y-axis which touches y-axis at E, and the second one towards x-axis which touches x-axis at point C. We'll be drawing one more perpendicular line from point A to BC which touches BC at point D. Now we know that this velocity time graph has not started from the origin, which is here. It has started at a point somewhere here which is not the origin, or which is above the origin in the y-axis. So this gives us an impression that the body has not started from rest. That means that it has some initial velocity. So this OA gives us the value of the initial velocity of the body. So our initial velocity we have taken as u. So this length we will be taking as u, that is our initial velocity. And since OA will be exactly equal to DC, since they are the two opposite sides of the rectangle OADC, so DC will be also equal to u. So here OA equals to u, which equals initial velocity of the body, and this also equals DC. Now the final velocity of the body is given by this length, that is OE. That is the final velocity of the body. And since OE equals to BC, BC will be also equal to the final velocity, that is V. So OE equals to V, which is the final velocity, which also equals to BC. Now OC gives us the time taken by the body to reach point B. So this we will be taking as T. Now we know that this graph shows that the body is in uniformly accelerated motion. So let the velocity of the body changes at a uniform rate. This means that the body is moving with a uniform acceleration, and we'll be taking that uniform acceleration of the body to be A, let's say. Now from the graph we see that BC equals to BD plus DC. So BD when added to DC gives us the total BC. So here when we want to find BD, we'll be taking DC to the other side. So BD will be equal to BC minus DC. Now we know what are the values of BC and DC, which are V and U respectively. So on putting those values, we have BD equals V minus U. Let us take this equation as our equation number 1. We'll be using this equation later on in the derivation. So our equation 1 is BD equals V minus U. Now we know how to find acceleration from a velocity time graph. All we do is to find the slope of the graph. So here we need to find the slope of the graph AB if we want to find the acceleration, which is A. So acceleration is given by BC minus DC divided by OC. So here we know OC equals T, and BC minus DC gives us BD. So here acceleration is equal to BD divided by T. And we have already found the value of BD, which is V minus U. So we'll substitute that value here. So our acceleration A becomes V minus U divided by T on using equation 1. So on taking this T to the other side, that is the left hand side, we get AT equals V minus U. Now On interchanging the terms here, we get finally the first equation of motion, which is V equals U plus AT. Having our second equation of motion, which is otherwise called as the position-time relation. Now we already know what is the second equation of motion, that is S equals ut plus half at squared, where S is the displacement, U is the initial velocity, T is the time taken, and A is the acceleration of the body. Here I have a velocity time graph AB, which shows that the body is in uniform acceleration. Now, in order to derive this relation, we will be drawing a perpendicular from point B on x-axis, which touches x-axis at point C. Now, we know that the body has not started from zero velocity, but it had a certain initial velocity which is given by OA. So, our initial velocity is given by OA, which is U. And the final velocity of the body is given by the length BC, which we will take as V. So, BC will be equal to V, which is the final velocity, and OA equals U, which is the initial velocity of the body. Now, OC is given by the time interval in which the body moves from A to B. So, OC is given by time T. So, OC equals T, which is the time taken. Now, let the acceleration of the body A changes at a uniform rate, which is apparent from the graph here. And the displacement covered by the body, we will be taking it as S, let's say in time T. Now, from the graph, we see that the displacement of the body here is given by the area under the curve AB, or area under the graph AB, we can see. So here, the area under the displacement is given by the area under the graph AB. So S, which is the displacement, is given by the area of the trapezium OABC. Here OABC is the trapezium, and if we want to find the displacement of the body from A to B, we need to find the whole area under this graph, which is AB. And this area is given by the area of the trapezium OABC. Now, this shaded region, the area of the shaded region gives us the value of the displacement in this case. Now, let us draw a perpendicular line from point A which touches BC at point D. This construction has been made to find the area of the whole trapezium. We will be finding the whole area of the trapezium by first finding the area of the triangle and finding the area of the rectangle OADC, and then adding up these two areas. So that's the procedure that we are going to follow to find out the displacement. So let's move ahead. So here S equals the area of the triangle ABD plus the area of the rectangle OADC. Now we know what is the formula for the area of the triangle as well as for the area of the rectangle. The area of the triangle is given by half into base into height. We will be taking AD as the base of the triangle and BD as the height of the triangle. And for area of the rectangle, we already know which is length into breadth. Here the length we will be taking as OC and the breadth is DC of this rectangle OADC. So let's apply that formula here. So S equals half into base into height plus length into breadth. So S equals half into AD, which is the base, into BD, which is the height of the triangle, plus the length of the rectangle, which is OC, into OA, which is the breadth of the rectangle. So this is the whole formula of finding out this whole area of the trapezium OABC. Now, this BD here is given by BC minus DC. When we subtract DC from BC, we get BD. So we will be putting that here. In place of BD, we will be substituting BC minus DC. We know the values of BC and DC, right? So that is the reason why we have made this substitution here. Now, we will be substituting all the values of this. AD, we know that it is equal to OC. AD is exactly equal to OC since it is the opposite side of a rectangle. So it will be exactly equal to OC. So AD is equal to T. And we know BC, which is the final velocity, equals to V. DC, which is the initial velocity, which is equal to the initial velocity OA, that is U, plus OC, we know it is T, and U is equal to OA, which is already given in the figure. So we have put all the values here in this equation. Now, S will be equal to half V minus U into T plus UT. On evaluating this expression, we'll be taking this equation as our equation number 1 and we'll be using this equation later on in this derivation. Now, from first equation of motion, we know that V equals U plus AT. So, V minus U will be equal to AT. So, let us take this equation as our equation number 2 here. We'll be using both the equations now in the process of derivation. So, this is our equation number 1, which is S equals half V minus U into T plus UT. And our equation number 2 was V minus U equals AT. Now, on substituting V minus U from equation 2 to equation 1 in this place, we have S equals half V minus U into T plus UT. Now, in this place of V minus U, we will be adding AT, which is from equation number 2. So, on doing that, we have S equals half AT into T plus UT, which gives us S is equals to half AT squared plus UT. Now, on rearranging the terms, we have S equals UT plus half AT squared. And this is our second motion, which is otherwise called as position velocity relation. We already know what is the third equation of motion, that is 2AS equals V squared minus U squared, where A is the acceleration of the body, S is the displacement, and V and U are the final and initial velocities of the body respectively. So here I have a velocity time graph which is AB. Now here, in order to derive this expression, we will be finding out the displacement of the body from point A to point B. So for that, we will be drawing one perpendicular from point B towards x-axis, and the point where it touches the x-axis, let it be C. Now, we know that the body has some initial velocity which we have taken as U. So OA will be equal to U, that is the initial velocity, and the final velocity of the body is given by the length BC of the body, which is V. And OC denotes the time taken by the body from point A to reach point B. Now, let the body covers the displacement of S in time t. So, in time t, let the body covers a displacement which is denoted by S. Now, the displacement of the body from the graph we can calculate as the area of the trapezium OABC, which is the area under the graph AB. So, it is this area. That is, this area of the shaded region gives us the displacement of the body from point A to point B. So, this is what we are going to find here. So, S, that is the displacement, is given by the area of the trapezium OABC. Now, we know that the area of the trapezium formula is half into base 1 plus base 2 into height, where we generally take the base 1 and base 2 as the two parallel sides of the trapezium. And here the two parallel sides are OA and BC respectively. So, we will be taking OA as base 1 and BC as base 2. And the height of the trapezium is given by the length OC. So area of the trapezium OABC equals half into base 1, which is OA, plus base BC, which is the base 2, and OC, which we have taken as height of the trapezium. Now here we'll be putting all the values in this expression now. So OA, we already know it is u, which is the initial velocity, and BC, we also know that it is the final velocity of the body, and OC is the time taken by the body. So on putting all these values, we have area of OABC equals half u plus v into t. Now this equation, let us take this equation as equation number 1. Now from the first equation of motion, we have v equals u plus at, from where we can find the value of t as v minus u by a. Now let us take this expression as equation number 2. We will be using these two equations to arrive at our third equation of motion. So the first equation that we have taken is s equals u plus v into t divided by 2, and the second equation that we have is t equals v minus u divided by a. Now we will be putting this value of t from equation number 2 in equation number 1 in this place, that is, we will be replacing this t by this expression over here. So on doing that, we have s equals u plus v into v minus u divided by 2a. On evaluating this, we get s equals v squared minus u squared divided by 2a. We have simply used the formula a plus b into a minus b, which equals a squared minus b squared. So that's the simple formula we have used here. So on interchanging the terms, that is on bringing 2a to this side, we have 2as equals v squared minus u squared, which is the third equation of motion. So this is how we derive the third equation of motion by this graphical method.